Alright, so for the next part of the ratio and root test, so we discuss the root test. But of course, we cannot talk about infinite series without talking about Ramanujan's spice formula. So this is a formula. I know it looks crazy. It's a formula that is used to approximate or to actually find the value of pi. Well, long story short, Ramanujan was a mathematician from India who actually he claimed he used to dream about gods and goddesses that will tell him sequences of numbers and expressions like this to find very interesting values. And well, so I mean, if you try to make sense about this, about this series, how did the 4n factorial times this linear, and well, this n factorial to the 4 power times 396 to the 4n, well, how do you make sense of that? And square root of 8 over 9801, well, try to find a sequence of numbers that follow this rule. I mean, without knowing this, for example, when we have like 1 plus 1, okay, 1 plus 1 half plus 1 4 plus 1 8, so that one is easy, so sigma n equals 1 or n equals 0 to infinity, and that's 1 over 2 to the n. That's powers of n, powers of 2 rather. But I mean, just imagine how crazy would this sequence look like, so you can figure out this rule. All right, well, of course, I mean, if you want to challenge yourself, you can use the ratio test to show that it converges. And of course it has to converge because it adds up to a value, in this case 1 over pi. Alright, now let's go to the root test. And for the root test, well, it's a similar in terms of how we conclude about convergence and divergence based on the limit or the value of the limit. It's the same as the ratio test, so if the limit is less than 1, well, converges absolutely, and if the limit is greater than 1 or infinity, well, the series is divergent and inconclusive when the limit is 1. Also, another comment right here, so this L right here, some books, I think our book uses the rho symbol from the Greek alphabet, so you might want to take in mind when you're doing the homework so you don't get confused with the symbols. Alright, so what we're going to do is to take the n root of the absolute value of the general rule that is given. Alright, so let's determine whether the series converge or diverge. So number 1, okay, we have sigma n equals 1 to infinity of the quantity 2n plus 3 over 3 to the n, the whole thing squared to the n power, not squared, to the n power. Alright, so this is what we're going to do. So in this case, limit n approaches infinity of the nth root of the absolute value of the expression right here, which is 2n plus 3 over 3n plus 2 to the n power, absolute value. And well, in this case, notice we don't have any alternating factors right here, so we can just go about the limit without the absolute value bars, right? So that's 2n plus 3 over 3n plus 2 to the n power. And in this case, notice how the index n cancels the power n, leaving us with limit n approaches infinity of 2n plus 3 over 3n plus 2. And computing this limit, well, we computed some like this before. Well, ratio of leading coefficients, because we have polynomial over polynomial whose degrees match. In this case, 2/3, that's less than 1, and in this case converges by the root test. Alright, let's do another example. So for letter B, what do we have? Sigma n equals 1 to infinity of n to the n power over 3 to the 1 plus 2n. And well, I would like to go back to the description of the criteria of the series, and this test is going to be your best friend whenever you have n powers. That's because those n powers get cancelled with the index n from the limit setup on the radical. Alright, so limit n approaches infinity of the nth root of the absolute value of n to the n over 3 to the 1 plus 2n. Alright, so and in this case, well, let's see what's going to happen here. So number 1, we may get rid of those absolute value bars because in this case we don't have any alternating all factors right here. So that's the nth root of n to the n over 3 to the 1 plus 2n. And we may use laws of radicals over here. So number 1, this is what I'm going to do. Or actually before doing the properties of radicals, I'm going to use laws of exponents to rewrite 3 to the 1 plus 2n as limit n approaches infinity. That's the nth root of n to the n over 3 to the first, which is 3 to the first, times 3 to the 2n. Alright, and well, in this case we may go about using properties of radicals. That is limit n approaches infinity, that's the nth root of n to the n over the nth root of 3 times the nth root of 3 to the 2n. Alright, in this case, well, how about we write number 1? Okay, on the one hand, this n cancels that n, and so we'll do for these two, but I think I'm gonna be more visual for the one in the denominator. So number 1, okay, the numerator limit, that's simply n over the nth root of 3, that's the same as 3 to the 1 over n. Recall that the denominator of the rational exponent is the same as the index of the radical in here, and the same happens here. So that's times 3 to the 2n over n, and in this case, see how the n's cancel. Alright, and well, so limit n approaches infinity. Oh, that's we're gonna be left with n over 3 to the 1 over n times 3 squared, which is gonna be 9. Now let's see, let's go about this limit. Number 1, we may go about it already, because well, in the numerator we're gonna be left with infinity over 3 to the 1 over n. 1 over infinity, isn't that a 0? 3 to the 0 times 3 squared, which is actually 9, which in this case will be infinity over 9 times 3 to the 0, which is 1. That's simply 9, which in this case, well, it's infinity. In fact, because infinity is greater than 1, the series diverges by the root test. Alright, let's go about a couple of examples more. Two more examples. What do we have? Sigma n equals 1 to infinity of n over n plus 1 quantity to the n power. Same. Limit nth root of the absolute value of n over n plus 1 to the n. And that's okay. Let's get rid of the absolute value bars in this case. You notice notice how we will be able to cancel the ends. Wow, that was rough. Limit n approaches infinity of n over n plus 1. Which equals to 1. Oh, sorry about that. And in this case, test is inconclusive. So we need to go about a different test in this case. All right. So let's see about it. Now, other special limits that you might want to consider, and in fact you might want to use this special limits on your sheet of notes on your exam, because, well, if you're computing a limit like this on an exercise, either on the homework or on the exam, so these limits will require to do the whole L'Hopital's rule. In particular, those are the ones that you have to set the limit equal to some y value, limit n root of n, and approaches infinity. Remember how tedious it were to compute those limits when you have to set it equal to a y? Well, just use these limits, or either memorize if it's fine for you, or put it on your sheet of notes. Just use them. No need to show the L'Hopital's rule for this one. Alright, so let's go about one more limit. So limit k approaches infinity of, in this case, well, notice we're not using n, we're using k, so that's going to be the kth root of the absolute value of -2 to the k over k to the 10th power. Alright, so in this case, well, let's rewrite this -2 to the k as a kth root, well, number 1, absolute value of -1 to the k, 2 to the k over k to the 10th. Alright. And well, in this case, let's take the limit. Okay, number 1, what you might want to do here is cancel or just eliminate this alternating factor and limit k approaches infinity 2 to the k over k to the 10th. Alright, now let's use properties of radicals in here. So number 1, the radical of a quotient is the same as the quotient of the radicals. Alright, so in this case, well, number 1, again, I didn't press this. In this case, well, so cancel the case, And what I'm gonna do, okay, number one, let me write down the property of radicals that I'm gonna use. So this k, okay, let me state the rule. Nth root of a to the m is the same as saying the nth root of a to the m power, and I'm going to apply this to the denominator right here. So this will be the limit k approaches infinity. Well, in the numerator we have a 2, and that's k root of k, the whole thing to the 10th power. And well, like I mentioned before, this will be one of these special limits. In particular, we're going to have this one special limit that is nth root of n that goes to 1, which is what we have. Kth root of k, and this limit will go to 1 because of this special limit right here. Alright? And well, in this case, our final answer right here will be 2 over 1 to the 10th power, which is 2 over 1, which is 2, and happens to be greater than 1. And because it's greater than 1, diverges by the root test. And this was our last example.